Hello everyone, my name is Maxwell Helm. I am a third year here at Georgia Tech, and I am in the A4Y group of AE 2610, Intro to Experimental Methods. Today I have a presentation on a recently conducted experiment performed by my lab mates and I on the Rijke tube. The Rijke tube falls into a broader category of something known as a pulse combustor. In a pulse combustor, the combustion intensity and the chemical heat release rate oscillates periodically with time. There are three major parts of interest in a pulse combustor: the heat release caused by the combustor, the oscillations of the pressure in the combustor caused by the fluctuating heat release, and finally, the acoustic velocity that is applied to the mean flow rate through the tube. These three major parts are important as they feed off of one another and are able to support one another until a balance is reached in the acoustic input and output of the tube and it's able to reach resonance. As previously stated for this experiment, we will be using a pulse combustor called a Rijke tube, named after P.L. Rijke, shown to the right. As shown in the figure to the right, the Rijke tube is a long vertical tube open at both ends with a burner, or some sort of heat release, placed at roughly 1/4 of its length from the lower end. Since this tube is open at both ends, if it is acoustically excited, it will act similar to an organ pipe, allowing the pressure in the pipe to become time varying and making a neat sound. So why do we even care? Pulse combustors actually have some benefits over normal combustors. You have better mixing of fuel and air, leading to more intense combustion. You are able to transfer much more heat through the walls, as the otherwise present insulating layer of the tube is stripped away by the acoustic velocity. And finally, the pulsations of the combustor will push out any exhaust components that in a normal combustor would have to be dealt with in some other way, making pulse combustors much more simple and privy to reduced heat loss. We'll be using two major pieces of measurement equipment: the piezoelectric pressure transducer, which takes advantage of the piezoelectric effect to measure the pressure experienced at different points of the tube, and the photomultiplier transducer, which is able to absorb and multiply photons generated by chemiluminescence of the reaction components, and therefore is able to show us the rate at which the reaction is taking place. Fast reaction, more photons, and vice versa. As seen to the right, we have a few equipment pieces for this experiment. The bottom right is the valves that measure the pressure of the fuel and help to modulate its flow rate into the tube. At the top right is the control panel that we use to modulate the height of the heat source, flow rate into the tube, and other aspects of the Rijke tube. On the left is the actual Rijke tube. To get started, we measured the Rijke tube, which ended up being 6 feet. We then hooked up the pressure transducers at 3 different locations of the tube, hooking them up to the oscilloscope that we could measure their readings, and then measuring the distance between them, which was 18 inches each, with a total span of 32 inches between the top and bottom transducers. After setting up the experiment, we initially took measurements at the base positions of 0 inches up the tube with the valve both open and closed. Opening the valve causes the flame to become much larger and less efficient, and ceasing the pulsations and the sound that is normally associated with a Rijke tube. But when the valve is closed, the sound resumes and the flow rate through the tube was increased, decreasing the flame size, making the burn more efficient and resuming the pulsations. After these measurements, we made sure the vent was closed, moved the burner up to 2 inches above the base position, and took the measurements there as well. We then continued to slowly move the burner up until the pulsations ceased, which happened at approximately 5.6 inches. Finally, although this wasn't measured, we lowered the tube until the pulsations resumed, which ended up being close to 0 inches and not at 5.6 inches as some people might expect. So as previously stated, the oscilloscope took 4 data points: 0 open, 0 closed, 2 closed, and 5.6 closed. It took 3 major data points for each of the locations. And these 3 locations were the upper, middle, and lower pressure transducers. Signal 1 is upper, signal 2 is middle, and signal 3 is the lower pressure transducer. Anyways, the 3 major data points taken at these 3 locations is the RMS pressure, shown as VRMS, the frequency, and the associated phase. There are 2 data reductions associated with this. The relative phase was taken from the associated phase relative to the middle pressure transducer by subtracting the associated phase for the middle pressure transducer from each of the other associated phases. Next, the amplitude in decibels was calculated from the below equation, where VRMS is equal to PRMS shown, and PRMS threshold is the constant shown below. Additionally, using the following equation shown below, along with the data we measured at the beginning of the lab, namely the temperature of the room at 73 degrees Fahrenheit and the length of the tube being 72 inches, we were able to calculate a resonance frequency of the Rijke tube at around 94 Hz. This makes sense, as if you look at the previously displayed graphs, when the frequency is not around 94 Hz, the amplitude in decibels is much lower, but makes a sharp increase when we get up to 97 Hz, which is much closer to the resonance frequency of 94 Hz. Now into the discussion questions. So the first one, we have a clumsy friend who accidentally drops the filter for the photomultiplier and is seeing if we can use another interference filter that's marked for 415 to 450 nanometers. This wouldn't work out, as the interference filter is a bandpass filter, only allowing wavelengths of 415 to 450 nanometers to pass through, which wouldn't make any sense, as the wavelength of OH molecules chemiluminescence, which is what we're measuring with the photomultiplier, only ranges mostly between 306 to 311 nanometers. But if we used a 415 to 450 nanometer interference filter, we would filter out all of that chemiluminescence, and we wouldn't get any of that. The next question is wondering if we could accommodate that if we were to use hydrogen as fuel. And based on my research, the chemiluminescence of hydrogen ranges around 425 nanometers, which would not be filtered out by a 415 to 450 nanometer filter, allowing us to actually complete this research project. So the next one is that we want to design a Reiki tube that's tunable. And as a brass instrumentalist, I had a couple ideas. First of all, you could fit it with a match ground sliding valve on the top side of the tube that you can move up and down and alter the length of the Reiki tube. Or something that happens with brass instruments is based on the temperature outside, whether it's hot or colder, you have to tune your brass instrument to that. So something that we could do is change the temperature around the Reiki tube to change the resonant frequency of it as well, or some combination of these two. So finally, for our conclusion, I thought this experiment was a pretty interesting one. It was very dissimilar to other labs we've done so far, as this material is unfamiliar to me and pushed me out of my comfort zone. If I was to repeat this experiment, I would try to achieve a more in-depth understanding of the material, because as I do understand this material, I feel that the uses and innovations of such systems come from a deep understanding that I'm still working on. In future experiments, I would be interested in testing out different modulation systems for the Reiki tube, such as the aforementioned match ground sliding tube or differentials in temperature around the Reiki tube to alter their resonant frequency. Anyways, that's all I have. Thank you for listening to my lab report, and I really hope you enjoyed it. Have a good day. Thank you.